Good evening, everyone. Thanks for joining with us. My name is Meenakshi Ponshankaran. I'm a senior big data architect with AWS for the past 3 years. I have Sampath Kumar Velusamy, Director of Technology FINRA with me. And we are here to speak about scaling EMR at the speed of market volatility. And before we get started, I have two questions. How many of you have you worked with EMR clusters of sizes 400 or 600 nodes? How many of you have used Apache Spark for their batch processing? That's great. So we all have processing deadlines. We have use cases that needs to be completed in a specified amount of time, and we have to deal with the business process in those the allotted time frame. And when a processing deadline is combined with unpredictable and huge volumes of data, it becomes a challenge. And today, we're going to speak about who's FINRA, what is Consolidated Audit Trail, and how did FINRA build an application that processes billions of events per day at scale. And what are the lessons learned while we build this application and optimized it to scale at the growth of the market. With that, I'll hand it over to Sampath, who will talk about the application architecture and lessons learned from the application architecture. Over to you.
Thank you, Meenakshi. Hello, everyone. My name is Sampath Velusamy. I'm a director at FINRA, managing CAT, Linker, and ETL projects. I'm very excited to be here to talk about how FINRA processes billions of market events every day and deliver the feedbacks in 4 hours to the data reporters. Also, I want to talk about the challenges that we had in implementing such a complex system and how we solved those challenges in the last 2 years. So we have a lot of content to cover today. I'm going to get started with some introduction. So who is FINRA? FINRA stands for Financial Industry Regulatory Authority. It's a regulatory organization authorized by government to regulate broker-dealer firms and brokers. Our mission is investor protection and market integrity. We ensure that every investor can participate in the market fairly and honestly. We regulate 3,400 broker-dealer firms and over 620,000 individual brokers. We work with 32 exchanges to get the trading activities from all those exchanges. We process 600 billion, more than 600 billion records every day, and we collect 130,000 files from broker-dealer firms and exchanges. And our storage footprint is one of the largest in the financial services industry. We have about 500 plus petabytes in our data lake. We create more than 9,000 clusters of varying sizes every day with a total EC2 instance capacity, instances of over 300,000 instances. We process thousands of data ingestion jobs and hundreds of ETL jobs on those clusters. What is Consolidated Audit Trail? In response to May 2010 flash crash, Securities Exchange Commission, SEC, adopted a rule asking exchanges, all the exchanges that operate in US and FINRA to create a plan to build a consolidated audit trail system. So this consolidated audit trail system helps regulators to easily track the market activities and use the data to analyze and find any market manipulations or any other activities that's happening in the marketplace. FINRA was awarded this contract in 2019, and we built this system in 2 years. Most of the functionalities were delivered in 2 years, and we are working on the last phase of the project. So why is CAT so complex? We get billions of data every day from broker-dealer firms and exchanges, and we have to process the data and deliver the feedback in 4 hours. So if you look at the timeline, both firms and exchanges, they have to submit all their trading activities that happen today by tomorrow, 8 a.m. Once we get the data, we have 4 hours to process and deliver the results to broker-dealer firms and exchanges. So it's a very tight SLA, so we have to process everything in 4 hours, billions of records in 4 hours, generate the feedback, and deliver to all the firms. So how do we do this? So this is a high-level process flow. You can see broker-dealer firms and exchanges, they submit the data to CAT system. Every file that we ingest to CAT is validated in 2 stages. So we validate the file itself, make sure that the files are named as per the requirement, file sizes are within the allowed limit, and the file compression is as specified in the specification. And once the file validation is complete, we open the file and perform the record level validation. Every record goes through validation. We validate for data type, data size, and allowed values and some conditional validations. Good records are accepted for further processing. Bad records are returned back to the reporters. Good records will go to the next stage of processing, which is the linkage validation process. In the linkage validation process, it's a linkage discovery phase where we find every secondary event, find its parent event. So this is the critical job in our CAT processing. So we have only 4 hours to process and deliver the feedback to all the reporters. So after the linkage validation is complete, both the feedbacks go to firm. Linkage validation feedback and the ingestion feedbacks are reported to firms. And firms have 2 days to fix their issues. So by T+3:8 a.m., they have to correct their linkage errors. CAT allows 1 more day to accept late corrections. So by T+4:8 a.m., they have to fix all their issues, ingestion issues as well as the linkage issues. T+4:8 a.m., after T+4:8 a.m., we start assembling the lifecycle. So this lifecycle process is a very iterative process. I'll cover that in the architecture slide. I want to explain what is a lifecycle with a simple example. I'll jump to the next slide. So this is a very simple example of a customer order lifecycle. You can see there are 2 venues here, firm A and exchange A. Firm received a customer order to buy some stock. Firm created a new order entry in their system, and they routed that order to an exchange. The exchange accepted the order, and they waited for that order to execute. After some time, due to price mismatch, the order did not get executed. Order got canceled. And finally, the order got canceled at the firm side as well. So there are 5 events in this lifecycle. There are 2 venues. So if you look at the intra-firm linkage, the events that happen within that firm are linked first. And the events that happen within the exchange are linked next. And then the second phase of this process is called the intervenue linkage. That's when we connect firm and exchange data. Then the lifecycle becomes complete. So if you look at this lifecycle, it tells you the flow of a customer order, how the order flow through the firm and exchange and finally got executed or canceled. And once this lifecycle assembly process is complete, we enrich the events that we received from the firms and exchanges and with the lifecycle information and few other information, and then we make the data available for the next stage, which is the use disseminate stage, where firms and exchanges and the regulatory users, they can use the query tools to access the data. So this is the high-level overview. How did we implement this system? So the technology stack that we use here is not very complicated. For ingest, we use CAT file transfer, AWS file transfer service, and we also have a web application to accept firms' trading activity through the web, through a UI. But most of the submissions come through SFTP channel. And for processing, we use EMR and Lambda. And the code is written using Spark and Scala. We support 3 file formats internally, text, Parquet, and ARG. All the internal Spark outputs are written in Parquet format for better performance. Final output, the consumable objects that regulatory users use, are generated in ARG format because the query tools need in that format. And for the query tool users, we have web UIs where users can go and enter their search criteria, and then they can submit the query. The query gets executed on the back end on an EMR cluster, and the results are showed on the UI. And we also provide a SQL client. That SQL client uses Presto as the SQL engine to run and return the results. This is used mainly for ad hoc query purpose. And finally, data catalog. So this data catalog is an in-house product we developed and open sourced it a few years ago. So it's called HERD. HERD is a unified data catalog which helps to manage the data that's sitting in the data lake. It's a centralized, auditable catalog for operational and governance use. All applications interact with this data catalog to find the source of their object or the files that they want to process. And once the processing is complete, they interact with this data catalog to register the data that they processed. And there is a data catalog viewer. Using the data catalog viewer, a user can see what objects are available in the data catalog. And for the selected objects, they can see the schema of the object, and they can see the lineage information, like what sources were used to generate this object and what the downstream objects are using this object as the source. All this information we can get from the data catalog viewer. Right. So I'll talk about the ingestion architecture. Both firms and exchanges, they submit the data to CAT. Firms, they use the SFTP channel to submit the data. Exchanges, they submit the data directly to S3 bucket. So we created S3 buckets for them and given access, so they upload the data directly to the S3 bucket. So every file that CAT receives is registered in the data catalog. In the data catalog, once the file is registered in the data catalog, it sends a notification. And this ingestion application created a queue. It's called the files to be processed queue, file meta queue. And all those messages will go to the queue. And then we launch a Lambda function to read from the queue, and we decide whether the file has to be processed on EMR or Lambda. because Lambda is fast. You can create a Lambda function and process the file. EMR, there is a provisioning time. So files that are less than 10 MB are processed through Lambda. Files that are greater than 10 MB are processed on EMR clusters. We encourage firms to submit the files, smaller files, so that they'll get the feedback from us immediately. And as part of this validation process, we also assign a numeric unique identifier for every record that we received. We receive 200 to 300 billion events per day, and we have trillions of events sitting in our data lake. All of them have a globally unique ID. And once the validation, so the validation, whether it runs on EMR or Lambda, they all have the same validation rules. They go through the validation process. Good records are accepted, bad records are rejected. We create two files, accepted file and rejected file. Rejected file is sent back to the reporter. Accepted file is stored on S3, and that is available for next processing. So the next processing is the actual linkage validation process. This is the critical process in our pipeline. We take the accepted data, perform the linkage validation. So we create EMR clusters of 500 nodes or 600 nodes, depending on the volume, process the data, and we generate the linkage errors as feedback files and deliver them to firms and exchanges. The feedback file for firms goes through the same SFTP route, and the feedback for exchanges are delivered through S3 buckets. Once this process, linkage validation process is complete, that's the 8 a.m. to noon process. So we have to deliver the feedback by noon. And then we'll wait for 3 days for the corrections to come in, and then we start creating the life cycles and then enrichments. All those things run on EMR clusters, massive EMR clusters, 500 or 600 nodes clusters. And all the process data stored on S3 and registered in our data catalog, that's available for regulatory users. So what are the challenges in building such a complex system? CAT has challenges in all aspects. Performance is a main challenge for us because we have to complete the process in 4 hours. There are many reasons that could impact the performance, right? Data volume, sudden spike in the volume, and the application itself is complex. There are hundreds of linkage rules. So this process has to go through all those linkage rules. Data skew could impact the performance. And from random spark issues, due to volume, you may get random spark issues that could impact the performance. So those are performance-related issues. And resiliency, right? CAT process billions of data in 4 hours. We don't have time to lose even 5 minutes. The job has to recover immediately and start processing from the step where it failed. And scalability. Market volume fluctuates based on the market, right? So if there is a 5% drop in S&P or Dow Jones, we'll see like 40 to 50% increase in our market volumes. And also, year over year, we see 20 to 30% volume growth. So scalability is a challenge. We have to scale to any given volume and process within 4 hours. Cost. As the volume goes up, cost also goes up, right? So volume, if 30% increase in volume means we have to use 30% more capacity, compute instances, and there is a storage cost associated with increased volume. But our goal is to keep the cost same or lower by using better hardware and optimizing our application. All right. So with all these, non-functional parameters, right? We have resiliency, scalability, and application performance. All these non-functional parameters are very critical to achieve the SLA. Adding more capacity to the process or the job is not going to improve the performance of your application if the application is not able to scale linearly. So it's a balancing act. Application has to perform well. Resiliency and scalability, all of those have to be handled efficiently. So in the last 2 years, we did a lot of optimizations to meet this 4-hour SLA. So in the next few slides, I'm going to share some of the key improvements that we did in the last 2 years, which improved the overall performance of the system, and we are able to meet SLA consistently for the new peak volumes. When we started this project 2 years ago, we went with the non-progressive architecture. So what that means is we process all the data, the linkage validation process that runs between 8 a.m. and noon. So we wait for all the files to come in, and then we start the process at 8 o'clock, and we'll try to complete it by noon. Initially, when the volumes were low, it was fine. We were able to process and deliver the feedback. When the volume increased, we were not able to process and meet the SLA because we are processing after 8 a.m. There is no pre-processing happening. So how did we solve this? We went with a progressive architecture where we process 80% of the data before 8 a.m. Certain linkages can be done before 8 a.m. if a firm submitted all their transactions to CAT. If they're completely done with their submissions, we can do the intra-linkage. The linkage that happens within the firm can be done, and we can keep the data aside, right? So we started processing in 2 batches. So we looked at the file arrival pattern for the last 6 months or 1 year. Based on that, we came up with a schedule. Midnight, we process the first batch, where 50% of the volume is processed in the midnight batch. So which means firms submitted data, almost 50% of the firms submitted their data to CAT by midnight. And then we run another batch at 4 a.m., where we process 30% of the submissions. So overall, 60 to 80% of the submissions are processed before 8 o'clock. So now 8 o'clock comes, we have only 20% to process. So this 20% intra-linkage has to process, and then we perform the inter-venue linkage and then publish the feedback. This improvement, the change in architecture and the schedule, helped us to save 2 hours, almost 2 hours in our 8 a.m. to noon processing. So it's a big win for us. So the key takeaway from this is, look at the architecture. If you have a massive data processing application with a tight SLA, look at your architecture and see what you can process ahead of time before the core hours, and minimize the amount of data that you have to process during the core hours. You can look at the business process and your process pipeline and see what optimizations we can gain, what can be done before the core hours. The next improvement is the Spark version upgrade. When we started 2 years ago, we were using EMR version 5.2.7 and Spark version 2.4. Those versions, so at the time, for those volumes, we were fine. We chose this version, and we didn't have major issues during the initial days. And after a few months, we started seeing problems because of the volume. Because there are some open source bugs in the 2.4 version. We get random log4j errors, and then Spark speculation had an issue, so we couldn't use Spark speculation for better resiliency and performance. So we had to upgrade to new version. So we looked at the new versions that are available at the time. EMR 6.5 was the latest version, and Spark 3.1 came with EMR 6.5. And simply upgrading to this version and using new instance types, the NVMe-based solid-state disk-based EC2 instances, just by upgrading to the new version, we were able to get 30% performance improvement. And also, with the new version, we have new capabilities, right? New instance types are available for us. We can use the new instance type, cheaper instance types, right? So that's another improvement that we did early this year. So the takeaway from this is, I think we should have a regular cadence for upgrading our software. Like, every 6 months or 1 year, we should upgrade to newer versions to take advantage of the performance that comes with it and also the bug fixes that comes with the new version. So the next one is the CAT application challenge. This is related to Spark Shuffle. Those who are working in Spark or worked in Spark, they know Shuffle is bad for performance, right? Because it requires better I/O, because it has to transfer the data. It has to transfer the data from one node to another node, right? So this linkage process has multiple group-by operations. Every group-by operation triggers a shuffle operation. And we have about some linkage keys have over 100 terabytes of data that we have to shuffle. We were using EBS-backed instances at the time, and the IOPS was saturated on the EBS volumes because 100 terabytes of data shuffling between the nodes was a heavy I/O operation. So how did we fix that? So we looked at the NVMe-based instances. NVMe is good for both random I/O access and also sequential I/O access. And it provides better IOPS for the shuffle-related works. We used Graviton instance types. So we benchmarked 3 or 4 instance types that are using NVMe-based disks. And we picked Graviton because Graviton gives best of both worlds, right? It has NVMe disk, and also it's cheaper. So we used Graviton, and we had 30% improvement after moving to Graviton, and also the cost-wise, over 50% saving for us. So the next challenge is the resiliency, right? Before we talk about the problem, I want to quickly talk about our orchestrator. So we created an in-house orchestrator which has all the features of the open source orchestrator. So we use a Lambda function to trigger the jobs. It takes the job parameters. We take the job parameters, and we have a standard template, step function template, which takes those job parameters, and then it launches the EMR cluster, and it adds the step to the EMR cluster. And it's a Spark application. The Spark application runs on the EMR cluster. The way we design the application, it's a single application, single Spark application. It runs for an hour or 2 hours or 3 hours, depending on the volume. And if there is a failure at the end of the 3rd hour or 2nd hour, the entire job fails. If we have to restart, we have to restart from the beginning. That won't work for us. We have only 4-hour SLA. We cannot lose 2 hours of work that we already completed, right? So how did we solve this? So check resiliency by checkpointing and restart. We checkpoint at regular intervals. So we've broken the application into small steps. And after every logical step, we checkpoint the data. We have 2 options to checkpoint. You can checkpoint on EMR, or you can checkpoint on S3. There is a cost associated with checkpointing, right? So there is a right time, 3 or 4 minutes for this massive scale. There's a 3 or 4 minutes of time, but that's worth spending. We don't want to lose 2 hours or 3 hours of processing. So we can afford 3-4 minutes of checkpointing time. So after every stage, we checkpoint. We checkpoint on EMR in some cases, in HDFS. We checkpoint on S3 in some cases. So that's up to our requirement. Like if we want to start the next step on a new cluster, you can checkpoint on S3. And also, if you have dependent jobs that is expecting data from this job, you can checkpoint on S3 so that 3 or 4 jobs can use the same data. And we track the status of the steps in a DynamoDB table. So that keeps track of which steps are completed and which are failed, stuff like that. So just to summarize, checkpointing at regular intervals helpful to recover from failures, right? And we checkpoint after every logical step. Each step is not more than 30 minutes. For our use case, that's how we decided. And restart. We restart, we maintain the state in the DynamoDB table, and then we restart based on the failure, right? We restart automatically. The having automatic restart is helping us. We almost like in our experience, more than 50% of the restarts, the failures, the first-time failures were completed successfully after the restart. So we don't have to manually intervene and see what failed. So just have an auto restart. The job restarts automatically. So we cannot stop just by optimizing the application, right? So we have to optimize the infrastructure. What if the application is scalable, but the infrastructure is not available or it's not optimized? So with that, I will hand it over to Meenakshi. He will talk about how infrastructure were optimized for scalability and resiliency. Over to you, Meenakshi.
Thanks, Abid. Thanks, Abid. Thanks for sharing information on optimizing application architecture for better performance and resiliency. For any application with tight processing deadlines, in addition to application performance and resiliency, your infrastructure as well as AWS services has to give better performance and resiliency as well. With that, during the initial days of processing, we started encountering a resiliency problem, underperforming instances. FINRA, on an average, creates about 300,000 instances per day. And what that means is they will land on every server in an availability zone at some point in time. And with that probability, there is always a chance of landing on an instance or a physical server which has a known issue or an unknown issue that is manifesting in those servers. These are hardwares, right? So you tend to have known problems or unknown issues manifesting in those servers. And every time we encounter an instance which is underperforming, and what do I mean by underperforming is we expect it to finish the processing in certain amount of time, and those instances are not doing that. We were impacted by 15 to 20 minutes. 15 to 20 minutes for every instance is very critical for us. In a 4-hour time frame, that's 10 to 20% of the processing time wasted because of retries and the straggler tasks. And when we encounter this underperforming instances, there are 3 symptoms we are normally impacted by. The first one is fetch failures. As with any shuffle process, the mapper process creates the temporary files, the output files, which a reducer have to fetch to complete a shuffle process. And we started seeing a lot of fetch failures on the instance which is underperforming. That was a very first impacting behavior that we started observing. The second behavior that we started observing is inconsistent task performance. In a Spark stage, on an average for us, anywhere between 10,000 to hundreds of thousands of tasks will be there on a stage. And what we started observing is the task performance, the 75th percentile or the 95th percentile performances were deviating a lot. And we saw all these tasks which are running slower originated from a common instance. The last behavior that we started seeing is stuck tasks. The executor has completed the processing. It has communicated back to the driver, but the driver thinks the executor is still working on those nodes. And the communication between these two are broken because of an underperforming hardware again. Now, is this a problem we can solve? There is always a probability of having hardware with known or unknown problems. And it is very important to build your application with resiliency and fault tolerance so that we can digest those underperforming hardwares and keep the processing moving. We started implementing workarounds from a resiliency standpoint. The first important workload that helped us is choosing a proper instance type. We migrated our workloads to Graviton-based instances, which after migration, we saw reduced error rates. With reduced error rates, better stability of the overall job performance. The second important workaround that helped us is EMR upgrades. The EMR upgrades, with EMR upgrades, we get new version of Spark, where a lot of resiliency and scalability related new features have been implemented or existing problems have been fixed. And that bug fixes helped us solve the problem of communication gap break between an executor and a driver. So that helped us a lot. Did we stop there? The third important configuration, the optimization that we started working on is configuration optimization, both at job level and also at cluster level. And one of the important configuration that helped us solve this inconsistent task performance is speculation. Speculation is a feature in Apache Spark on which the Apache Spark engine will execute the same task in 2 different instances. And whichever the task that completes first or faster is accounted, and the task that completes slower is neglected. Now, what we were able to eventually do with this feature is remove the bad node or the slow node or the underperforming instances from the overall processing itself. Because the same task is processed on 2 different nodes, we were not impacted by the underperforming hardware there. And this second configuration that we started looking into is we want to exclude not just run the processing in 2 different nodes, but we also wanted to exclude the instances from the overall processing in the next subsequent stages. We know this stage is impacted. Why use the same instance in the next stage? And again, Spark has another feature called exclude on host. There are a lot of heuristics you can play with, and we optimized our configuration based on the impacts that we wanted. And with the help of configuration, we were able to exclude nodes from processing for that particular Spark application. The last thing that we started building is, in addition to optimizing the cluster configuration, application configuration, using new instance type, we also build monitoring capabilities. We started building our custom monitoring capabilities, which will monitor these bad instances. And we also automated using AWS SSM agents to remove those bad instances from the cluster. While the processing is happening, on the background, the SSM agents will go ahead and shut down the node manager and data node on those process, and EMR will eventually remove those nodes from the cluster. So to understand the trends on which we were impacted, right around December and early January this year, we were impacted about 40 to 20 times a day. And to put it in context, FINRA create on an average about 300,000 instances, which means 5 to 6 million instances per month. So 43 instances of 5 million is very negligible, but in terms of impactness, it's significant. Every time we get an underperforming instance, it's 15 minutes for us. But after the upgrade and Graviton migration, and also fine-tuning speculation as well as exclude on host configuration, the impact has reduced significantly. We are either one or two occurrences a day, a month, or 0 occurrences a month. And we have the capability to withstand 1 or 2 impacts a day. With resiliency on application and the infrastructure sorted out, the next important challenge we encountered is scalability, handling burst writes on an S3 partition. Typically, an S3 offers 3,500 puts and 5,500 gets per prefix. And FINRA's S3 prefixes follow a traditional hive partition model. What that means is you have the partition field and its value in the prefixes. And with that, the data is always partitioned by either a processing date or a trade date. And we have multiple workloads accessing the same trade date or a processing date level, data sets within a trade date or a processing date level. And because of multiple parallel workloads accessing the same prefix, with EMR and Apache Spark, the traffic towards those prefixes increase. We need higher throughputs for the prefixes for those prefixes at partition level, at trade date or processing date, and we started saturating those prefixes. Once we started saturating the amount of throughput that each prefix provides you, we started seeing 503s, slowdown errors. And with slowdown errors, it not only impacts your performance, but also job resiliency and stability. We started seeing job failures. How did we solve this problem again? The first thing we started doing is we collaborated with S3 service team to understand what are those prefixes which are impacted by 503s. And with the help of S3 team, we were able to partition those prefixes in a specific way so that the throughput on that prefix level increases. The next important feature that we worked with EMR service team is additive increase, multiplicative decrease retry policies. By default, EMR comes with exponential back-off retry policies. And with AAMD retry policy, AAMD is an algorithm used on TCP congestions. And what EMR does is, if there is bandwidth available at a particular prefix, you can increase your request rate. It will automatically increase it. And the moment we start encountering 503s, it will automatically decrease the request rate. And after moving some of our workloads to use AAMD retry policy, the 503s came down by 79%, which is in terms of very significant for us. We were facing millions of 503s, and 75% reduction gave us the stability that is needed for our jobs. And with the reduction in the 503s, not only stability, the performance also to an extent for certain workloads, it improved. We also looked at managing our workloads. One of the important areas that we looked at is partition pruning. We made sure that when you have concurrent workloads accessing the same partition date, we wanted to further partition it even further down and see if we can reduce the amount of data that is being processed at a job level. We started optimizing the file sizes. We standardized 128 MB to 1 GB of file sizes with Parquet as the file format. And by doing so, we reduced the number of S3 objects, and that eventually helped us reduce the 503s. And the last optimization that we started doing is we started working on with the help of the orchestrator that we built, we started working on scheduling these applications in such a way that we reduce the impact of the reads, concurrent reads and writes at a prefix level. Now, the next scalability challenge that we encountered is capacity. At 8 to 12, typically we launch clusters of sizes ranging from 100, 200 nodes to 600 to 800 nodes. And we don't have single cluster, we have multiple clusters running at the same time. And what we started encountering is capacity problems. With 4-hour tight SLA, we don't have the bandwidth to be iced. Insufficient capacity exception. We don't have the bandwidth to be impacted by insufficient capacity exception. So guaranteedness, capacity guaranteedness is very important for the overall processing. How do we achieve capacity guarantees? We started leveraging on-demand capacity reservations. For all the critical workload, we started reserving instances using the ODCR capabilities. And the next problem we started once we reserve the instances is, we wanted to make sure these reservations are used by our critical workloads. We don't want a non-critical workload to hijack or use the reservation and the critical workload again get impacted by that. And that's when EMR team came back with the support of targeted ODCR. So EMR can now support targeted ODCR, targeted on-demand capacity reservation, and you can target a specific workload to use those reservations. And with the help of targeted ODCR, we were able to manage the reservations effectively and keep it use it for the critical workload. And on the weekends when the processing is not happening, we suspend the ODCR and then we resume it back when we needed it back. So we started improving performance, scalability, resiliency. We started processing at huge volumes of data. The volume increased, and we are still able to process those volumes of data. And as we increase more clusters and as we improve the overall application efficiency, we also wanted to make sure we are keeping cost under control. And one of the important cost optimization that helped us is migration to Graviton. With the EMR upgrade enabled us to use Graviton instances. With 5.2.7, we were not able to use Graviton, but once we migrated our workload to 6.5, it opened up new instance possibilities, and Graviton is one of them. In addition to performance, after migrating to Graviton, for the intra linkage process, CAT linker specific to linkage process, we saw 60% overall better per price performance. We spoke a lot about critical workloads. We also have workloads that run outside of the 4-hour window. And one of the common problems that we started seeing in those workloads is spot capacity. These workloads have instance fleet in their configurations with 1 to 5 instance types specified in those fleet configurations. And we try to use spot for non-critical workloads. And if spot capacity is not available after 30 minutes, then we fall back to on-demand. And with these workloads, with 1 to 5 instance types part of the fleet, we started seeing capacity problems with spot. And because of that, we eventually have to fall back to on-demand. And once we fall back to on-demand, our cost increased. And with not only cost, even with on-demand instance types, sometimes we got into capacity problems. We have 1 to 5 instance types, and the instance types that we were asking were not available. How did we solve that? So we started looking at instance type diversification. Again, early this year, EMR started supporting, instead of 5 instance types in a fleet, they started supporting up to 30 instance types in a fleet. And we changed our cluster definitions, configurations to include more instance types from more different families, part of a cluster creation request. CAT, now they have 5 to 15 instances depending upon what workload it is. And we also utilize allocation strategy, which is a feature in EMR and EC2, which helps you get capacities based on capacity optimized for spot and cost optimized for on-demand. It offloads the capacity from EMR to EC2 and gets you the capacity much better way. We started using allocation strategy, and after migrating after we started diversifying our instance types, we started seeing less cluster creation failures, and we also our overall success rate improved. We are still working through to figure out how to get to a better combination of those 15 to 30 instance types, but the success rate improved significantly after we diversified our instance type. With all these optimizations, early this year, we were either our SLA met percentage was very less. We were about December 40%, and January we didn't meet the SLA. With all these optimization, Graviton upgrade, and the capacity-related optimization, our SLA achievement increased. We are at 100% now, with the increase in 80 to 90% increase in volumes. January, we were about 100 to 200 billion records per day, but now we are about, this is just for the intra-linkage process, not the entire exchange, but for intra, our volume increased by 2 times, but still we are able to meet the SLA with all the optimizations. Did we just improve performance? No. With Graviton adoption and further optimizations of the application, our compute hours came down by 50%. We were at 800,000 compute hours on a daily basis. Now we are at 40 to 50,000 compute hours, which means we are processing more efficiently than what we were during the starting of the year. Did we stop? No. We are looking at new capabilities that could help us scale even further better. We are evaluating EMR and EKS, EMR serverless, and Apache Iceberg for scalability and resiliency. With the success of Graviton, we are looking to adapt Graviton 3 and EBS GP3 volumes for better performance. And we are looking at new versions of Apache Spark 3.2 to use features like magnet and new shuffle performances. And we are also looking at application modernization, where Progressive still does multiple batches at a time, multiple firms at a time. We wanted to parallelize processing by firms. Now, the key takeaway with that, the key takeaway that we want to call out is, for any application with a tight processing deadlines and huge scalability problem, it's important to have performance engineering part of your developmental lifecycle, with focus around not just on application, infrastructure, and scalability and resiliency. With focus on all those 4 layers, we should be able to build an application which can scale for higher volumes of data. You want to add anything, sir?
Yeah, I think when you are choosing the instance type, choose the right instance type for your workload. So if you have a compute problem, use compute optimized instance types. If you have Spark application which uses memory and does large shuffles, go for NVMe based instance types. And also have a regular cadence for upgrading your software, like every 6 months or 1 year. And design for scalability. That's design your application so that it can scale for any new volumes that you see, peak volumes.
Yeah, thanks everyone for your time. I think we were able to provide some value.
Thank you.
And we'll be available offline if you have any questions. Thank you.